Hi, I'm Roee. This is David Kaplan of IBM Security, and today we'll present an attack that we developed on the Linux PRNG on Android. Now, the story is that over a year ago, we detected a buffer overflow vulnerability in keystore, which is one of the most critical services in Android. This service is responsible of storing sensitive data such as the RSA private keys, VPN credentials, etc. So we reported this issue to Google. They fixed it in KitKat. And in order to create a working exploit, one has to overcome several defense mechanisms, including the stack canaries. So in order to overcome the stack canaries, there are a few techniques. The first one is a naive brute force of the canary value. This is very inefficient and impractical to do so online on the device. Other techniques require some more features of the target process, which is not the case of the keystore service. The first one is to abuse some other info leak issue in order to learn about the canary value. We couldn't find such issue in the keystore case. In the case of reforking a server, one can learn the canary value in linear time, 1 byte after byte. Again, this was not the case of the keystore service. Another technique is to somehow overwrite the global variable that the canary value is compared to using some pointer that is after the buffer. We couldn't find such pointer in the keystore service. So we had to take a different approach. So we decided to somehow reconstruct the PRNG state before the canary generation. So now I'm going to pass it over to David, who is going to explain how we did it.
Okay. So the first thing that we need to realize is that Android is simply a fancy distribution of Linux. And therefore, it makes use of the Linux kernel in order to generate the stack canary values. And just to get started, I'm going to give a brief overview of how the Linux kernel PRNG works without going into too much detail at the moment. This is true for kernel versions under 3.6, which is in fact what the majority of devices today use. Okay, so it's still very relevant. And what happens is that the Linux kernel is basically a cryptographically secure PRNG in two parts. The first part is a blocking part, which is something that doesn't really concern our research. But we focus on the non-blocking mechanism of the PRNG, which basically means that any consumer that extracts a value from the PRNG is assured that the PRNG will return some sort of value. And what happens is that the entropy, if you like, is stored within a pool, which is simply a buffer of bytes. And when a caller requests entropy or requests a random value from this pool, the pool is hashed, and there's a feedback mechanism in order to update the state. So it's pretty simple. So if you request a value from dev urandom or get random bytes call in the kernel, it will simply perform this hash and update on the non-blocking pool. And what happens is that if there is sufficient entropy within the input pool as determined by the kernel, so there's this kernel entropy count that kind of represents an estimation of entropy, and if there is a sufficient amount of entropy, 192 bits, then this non-blocking pool will, in essence, copy entropy from the input pool. So in order to attack this, we need to firstly understand how these pools are seeded. And the first thing the kernel does is simply seeds the pool of k-time value, which is the time since the system uptime. The next thing one needs to understand is, once the pools are seeded, what are the external entropy sources that may add entropy to these pools, to the input pool, during runtime of the device? And once we understand those things, we can start talking about our attack. So in regard to this work, there has been much prior art on this topic. For many years, it's been understood that there's a weakness in the Linux PRNG, especially in regard to early boot as a result of lack of boot time entropy. What we did is, to the best of our knowledge, we're the first that present an end-to-end attack on this. So a lot of people postulated that it's possible. In fact, we have the author of one of the first papers on this sitting in the audience here. But what we did is present an end-to-end attack and show how that's done. We also formalized the attack. And we present proof of concept, one which we'll show you today on a Galaxy S4 mobile device, and another one in a paper where you can, which you can see on an S2 device, which is slightly older. Okay, so our attack is as follows. So we say that given a leak, and I'll explain a bit what this means in a moment, but given a leak of some value from the PRNG, which means a leak from the non-blocking pool, and given that we have low entropy at boot, well, then we can determine the state of the PRNG until such time as external entropy sources make that indeterminate. Okay, so if it's not clear, it will become clear over the next few slides. The first thing we do is we run a simulation of the PRNG, which is basically just taking the kernel code, running it offline locally, and we feed inputs into that PRNG based on a set of candidate seed information. So these candidates are determined basically by instrumenting a target device, understanding what the variance of those candidates could be, and feeding them in the order of descending probabilities of those candidates in order to make an efficient search. We also compensate within the algorithm for any external entropy that may be added as a result of input or disk or any sort of other things that may happen. And then what we do is we need this leak value, which I mentioned earlier, which is basically any value that's been extracted at any point in time from the PRNG. So you just need to understand some value. And as Matthew said in the Klepto talk this morning, that there's no separation between the use of this for data and non-secret information and the use of PRNG for crypto purposes. So it should be trivial to kind of identify where this is leaked. And once we have it, we simply compare this leak with what's been generated from a current execution of our simulator. And if obviously it matches, then we've determined the correct candidate and entropy path. So just to show you what this looks like on an S4, a Samsung Galaxy S4 mobile device, what's interesting in most devices that we looked at, that in fact this kernel threshold where it pulls from the input pool is never actually reached in early boot. In fact, it's not even reached in late boot. It takes thousands of pulls from the pool in order to pull entropy from the input pool. So all we have to be concerned with in a practical trivial attack is the seeding value from the non-blocking pool. And this is a PMF where you can see kind of almost a normally distributed seed candidates, which is under 24 bits of entropy, which is something that's certainly reasonable in a reasonable amount of time. So the next question is, okay, we understand this candidate seeding values, but what is the leak value which we can achieve in Android? How can we have a value with which to compare to see if our simulation has worked? So just a brief introduction to how Android executes applications. When you execute an application, it's basically forked off this Android Zygote process, which is a process that is run at early boot. And as it runs itself in early boot, then the stack canary of the process is generated from the PRNG at that time. Basically, it takes the first 4 bytes of this 80 random vector, and any application that is executed will inherit the same 80 random vector because it's simply a forked process. This is a known weakness in Android Canary version 4.3, and we're not going to talk about that. But what we can do here is simply create a malicious application that extracts this 80 random value and use that value as the check value, as our leak value. In order to do this, we have 2 problems. Firstly, this is already a user-space process, so the Linux kernel is running in concurrent mode, meaning the scheduler can simply decide when to execute the different pools, the different extractions from the PRNG. So our first issue is we don't exactly know which process the Zygote process is for which to compare simulated results. It's simply solved because we just extract a set of data, many blocks of data from the PRNG, and perform a linear search. And if we find it, well, then we know our candidates are correct. The second issue is a bit more complicated. I'm not going to go into it now. Basically, again, because of concurrency, there's no kernel lock on kind of the mixing process, so there can be a PRNG state corruption, and therefore we can't predict exactly which path that extraction is going to take. But in fact, in 20% of the cases, we can know the path, and that's absolutely fine and pretty good for an offline attack. So just to show you a very brief demonstration, a bit difficult to see, but on the left of the screen, we have a screencast of the Samsung device running our malicious application. A bit hard to see, but you can see it's kind of extracted the 80 random value there. It will send that value onto our cloud server, which will perform the search over the entire key space in around 7 to 8 minutes, something that we've fast-forwarded here. And it will launch a set of worker threads. You can see it kind of running, the thread's running in about 10 seconds time. You'll see that it has found the seed. Give it a moment to execute. Okay, here we go. Okay, so it's a bit hard to see. It's kind of at the bottom there. It's discovered the seed. And then the next thing, obviously, we have to do is try recreate find out what the canary value of the key store process is, which was the whole point of this exercise in the first place. So what we do is we simply feed this candidate seed back into the simulator one last time to generate a list of possible candidates for the process. The value on the left is the value we expect. We kind of got that from instrumenting the device. And you'll see that, in fact, it's present in the list. So with a certain probability, and you can read our paper to understand further, we can predict quite trivially the value of the key store canary and any other canary. Okay, so just to sum up, so we demonstrated a trivial practical attack against an S4. Another remote leak, you could look at a paper. We looked at IPv6 and fragments, and we used that in order to leak the value as well. And even though this is old kernel versions and is mitigated in new versions, it affects the vast majority of Android devices in the field today, and they have no upgrade path. So it's a situation we're at. Thank you. Questions?
The typical dev random driver accesses a buffer of, I think it's 4K bytes, I'm not sure, that is saved from time to time and is pulled in as part of boot. So if that were working properly, this shouldn't work. What happened?
Okay, so the first thing to note is that we kind of formalized a generalized attack. So it's not specific to Android, but let me refer to that. In Android version 4.4, and in certainly more modern, newer devices like the Galaxy S4 on 4.4 and the Galaxy S5, what one would see is, in fact, that mitigation is used where the init process will save the state across boots. If an attacker knows that state, like can access the file system, well, it makes the point moot. So the attack's still theoretically valid, but correct, it is one of the recommended mitigations. It's not a particularly strong mitigation because you might have some other way of leaking that information. And it's only present on current, modern, newer devices. Okay, thank you.